Okay, streaming looks like it's working. Okay, all right, we'll get started in a second. This will probably last like 10 minutes tops. So for those who like to listen to live, you'll be in and out quickly. Those who came later, you'll be taking the same amount of time. So it's going to be okay. So 1 second. Haven't done this in a while. Whoa. Did some stuff before, huh? All right. Did some trigonometry. Did a little sine, cosine, tangent, SOHCAHTOA. Did a little Pythagoras and unit circle stuff. Got a ruler in there for a bonus. Not bad. Let's see here. Camera's here. Okay. And, ooh, this is good. I needed paper. So I'll use the back of this. Looks good. Got the standards for 8th grade math. We're almost through it. Doesn't say that we are passing 8th grade, but hopefully those of you who are listening, maybe you got lucky and you made it through grade school, so all good. Okay, I'm feeling this now. Oh, something's wrong. Oh, interesting. Oh, I think streaming is fixed now. Oh, that was weird. Okay. All right, sorry about that. Gotta watch this thing. I know it's easier to stream with the modern cloud-based systems, but I have this like piece of software I bought in business terms called sunk cost. So I kind of like to use it. So maybe I'll give up. Hello, Carrie. Glad you're here. I hope you're safe and healthy too. Okay, so let's get where we were. Put my music down here. Okay, so where have we been with Sometime Sunday? We did some math standards for high school. You know, we looked at this. You gotta know a lot of math to graduate from high school. Whoa, I'm getting like glitchy power. So just keep watching this. I've got like too much hardware for doing this. I kind of overshot my sort of whatever. So I'm gonna watch it. The video signal seems to go out once in a while. Don't know why, but I've got like a USB hub with 8 different things plugged in, so not surprised. Okay, so I gotta watch. Again, I'm not a YouTuber by training, just trying to play one once in a while. I use my computer, so I'm always like changing the computer, so I can't have a default setup. So works sometimes, doesn't work other times. That's why sometimes and sometimes Sunday. Okay, mathematical standards. We talked about rational and irrational numbers. We talked about functions, function boxes to stick numbers in. Magic. Talked about geometry, got into a little Pythagoras theorem. Like everything you want to know is in Pythagoras' theorem. It's like bizarre. Remember 3, 4, 5 triangle? Put everything together. You get like a quick way to figure out how Pythagoras' theorem works. You get from that how to calculate the distance between 2 points for free. I mean, like, wow. And got into little statistics. Statistics is a little bit not so easy, so that's what I want to like dig into a little bit. Also, I'm an old-fashioned magazine reader. Terrific article about John Lewis, rest in peace. Incredible civil rights advocate, hero. So please, let's remember him because he did a lot of stuff for all of us. Doesn't matter who you are, impacted your life. Okay, so streaming so far so good. Okay, let's see if I can multitask. Got any junk here, excuse me. Move this over, sweep it up over here. Okay, pen. Remember this money was the 8 bits. Remember 8 bits? You sort of calculate 8 bits. 8 bits also, 1 bit, 0 or 1, 2 states. 2 bits, 0, 1, 2, 3. That's a total of 4 states, right? And it gets hard after that because you can't count in your head too quickly. But if you have 8 bits, you can count from 0 to 255, mapping to 256 states. Super important thing. A byte is 1, 2, 3, 4, 5, 6, 7. Oh, I lost my special whatever. Oh, here we go. 8 bits, 256, super important number. For people who are like millennials or Gen Zs, you came a bit late because computers used to only show 256 colors. I mean, they didn't show any color, first of all, but 256 colors. The number was everywhere, 256. You don't see it so often because you live in the 64-bit, 128-bit generation, but the 8-bit world, 256, magic number, as important as 100. 100, like, we know 100, we know 10, but if you speak machine, 256, it's like 60 miles per hour or however fast you drive on the highway. So we won't get into that. I also made some dice. I have a 3D printer called a paper printer. So you'll see why I made this. Okay, all right, so then put the money aside. Okay, all right, this is paper. Okay, how are we doing so far? This sometimes Sunday thing is a good thing. All right, so let's talk a little bit about statistics. If you recall, if I drop a coin, it might be, think of this green dot as like heads or something. Actually, it is heads in this case. So, and that's tails. Tails. Heads. I'm not flipping it because I'll drop it. But anyways, you know what I mean? If I keep flipping and flipping and flipping it, you're not going to be able to guess what it is. But you'll be able to be right like half the time. If you keep saying heads, 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 you're going to be right half the time because there's 2 states. It's kind of magical in that way. And if that's what all statistics was about, it'd be kind of awesome, kind of easy to understand, but it's not. So what do? Like anything you read on machine learning throws in statistic, throws in all kind of cool symbols that you can't type easily. So you got really cool symbols. It's like, it literally is Greek. So what do? But it's pretty easy to understand this coin thing, right? It's like you flip it, unless it's like you're cheating or something and the coin is special, right? The coin is somehow rigged. Now, that word's meaning has changed. But, it's like you flip it, it's going to be heads or tails. Okay. Half the time. So let's pause for a second and ask a question about this dice. Now, this is not a real plastic dice or whatever dice. This is a John found a thing on Pinterest and printed it out, and you can see it's not well crafted. But so if I drop it, it's got a bias in it because I made it by hand. So if you really measure, it won't always be 1, 2, 3, 4, 5, 6. It won't be evenly distributed because it's got like tape and edges roughly. So it's kind of like rigging a dice basically. But you'd assume it has a behavior like the coin. Like if you were just to sit there and say like, if I ask you to guess like 1 to 6, go guess. And if you just said 1, 1, 1, 1, 1, 1 all the time, you'd be right 1/6 of the time. Okay, let's see if we're following me along. I actually had to do a project. Oh, yes, I used to do graphic design. As you can see, I do different things now. So thanks for that era. That was a fun era. Maybe I'll come back to it. All right. So, okay, following me? This thing has 2 states, the coin. This thing has 6 states. All right. So if I keep like flipping this, 50% probability that I can guess it. If I have this thing, I have 1 over 6. Can someone like go online and like just go Google 1 divided by 6? Let me get my calculator out. Let me be like proper. As you can tell, I like to make this up as we're going along. It's meant to be organic, like real. Like this is not like planned. 1 divided by 6 equals, of course, it's 16.6%. So, you know, I can guess this right 16.6% of the time. And I can guess this right 50% of the time. So think of horse racing, which I think is illegal in some parts of the world. So let's not use an example. That sounds amoral. So you're trying to guess how many eggs are in that recipe for that incredible cookie you just ate. You know, what kind of chance do you have to guess? Well, first of all, if you've never cooked or baked, you have no idea. You've never cracked eggs, put them into cookie batter or whatever. You're going to say like maybe 20. Whoa, I just lost my light. Okay, as you can tell, my AB technology is somewhat... Anyways, okay, we're still going. Signal is going out, all positive. Okay, so if you've made cookies before, there's a likelihood that you'll know that you don't need that many eggs. You're not going to guess 20. You might guess like 2 or something, especially if it's like in a small batch. If you're like making cookies for like a bakery, that you got to go 100. But if you're baking cookies for like a small household, whoa, glitch. I got this, as you can tell. Small household, there's a range of how you would guess that, right? So statistics, probability, it's really about being good at guessing. But if you're going to be good at guessing, you kind of want to have a hint, right? It's like, if you just guess randomly, totally randomly, good luck. So that's why having knowledge ahead of time is really good. There's also a thing if you look for something called Bayes' rule. This is like all over the machine learning world. It's like penicillin for data. So anyways, you can look at that later, but it's got some of that, like, you know, if you knew something about something and something is related to it, then if you knew something about it, then you know the chain of events with a higher likelihood. Seems kind of obvious, but you know, people who do math, they like make it look amazing with like Greek letters and stuff. Again, love mathematicians. This is not shade. You're here for the Sometimes Sunday Math Show. We're here to appreciate mathematics. So, not about that. Just trying to like make it flow for you because it's Sunday and a few of you are here. Hi, how you doing? Yeah, okay, there we go. So see, everyone's helping out each other because there's knowledge out there. We're just sharing. Okay, so where were we again? 50% of the time, 1 over 2. 16.6% of the time, 1 over 6. Okay, so again, if I wanted to guess 1, it's going to be 1 or 2. If I'm always guessing 1 or 2, I could kind of multiply that by 2, right, to be more right often. So, you know, you want to like figure out how many options you got, and you figure out what range of guesses you want to bet on. And if they're evenly distributed, you can really like up your odds, as they say. Oh my gosh, that's where that came from, right? So, okay, now why is this important? It's important because you see me flipping this coin, you see me like rolling this dice. Mathematicians think this, what used to think this is like, what is this? This is like wizardry, witchcraft. It's like, it's not real math. I know when I went to MIT in the 80s, statistics was kind of like, yeah, right. Like, yeah, you can flip your coin and you can have 100 events and good luck. It's not real science, it's not real math. But as you know, we live in the era of the cloud with many events inspecting our usage patterns. It's like data all the time. And statistics loves data. It's a way to guess really well if you have a lot of data. But I was finding how in the late 1800s, I don't speak French, but it's a cool French name. Poincaré? Poincaré. I guess if you like type in the comments, you can, because you can't sort of like rate the pronunciation. But this is him saying here, that's a great quote I found. Um, this is about the normal distribution, which we're going to dip into, and it'll be done 5-7 minutes. Normal distribution cannot be attained by rigorous deductions. Several of its putative proofs are awful. Nonetheless, everyone believes it, as M. Lippmann, clearly someone who came before Poincaré, because experimenters imagine it to be a mathematical theorem, while mathematicians imagine it to be an experimental fact. You feeling the math, science, STEM shade there? Whew, that burns. Okay. But again, that's 1800s, not a lot of data, people flipping coins, put them in a room flipping coins for like a couple days or 10 days. People get tired. Not a lot of data. But again, we live in the age of data. Always on data flowing to the cloud. Why are people afraid of TikTok? TikTok. Do they sell TikTok still? TikTok. And it's because, they're watching us. The Chinese are watching us, but Facebook's watching us, and Google's watching us, Microsoft's watching us. So I really well, I know there's this national border thing. I think I'll do a thing about like borders, whatever, with math. Got to find out how to put those two together, but I think it's important, at least for me to figure out. Again, thank you for joining Sometimes Sunday Math Show. You're here as I stumble through math concepts from 8th grade, and I'm going to go to 9th grade in the next one, in some future sometime Sunday. Okay, so normal distribution. What does that mean? I love it. So I'm sure all of you remember, I don't know, depends on the country, I guess, but when you were in high school or something, and they're like, you're getting graded. Do you remember you're getting graded? Like you get A, B, or C, and you get this test, and the teacher says something about like, there's like a distribution, a normal distribution, and that's like how we judge you, because there's kind of someone who's like kind of in the middle, and then you have what's called the first standard deviation, and like that's kind of average. And then as you kind of like leave these averages, you've seen figures like this before. They look much better and more accurate than what I've drawn. And I remember when I saw this in school, I was like, what is this? I can't stand this at all. But I think years later, it's sort of, I think all of you seem to know this better than I do. I kind of catch it. I understand it sometimes, some decades, other decades I lose the information. But this is something beautiful. I mean, this is, whoa, lost signal. 1 second. Okay, again, sorry. I have debugged this video setup for the last half a year and have never been able to get it right. But let's not complain online. That's my own dirty laundry. Okay, all right, yeah. So Tic Tacs. Adelaide. You know what I'm talking about. Okay. So this is called a normal distribution. And the problem with a normal distribution is, yes, again, just for you out there, my video comes in and comes out. I have 2 HDMI converters into my computer, and they just don't get along. And I've introduced them to each other like 2 cats, but they still don't understand each other. So anyways, okay. But we love the HDMI converters because they're producing high definition for you, right? Okay, so, and I'll just keep watching this from the side of my eye to make sure it's working. Okay, normal distribution. So what's the problem with this naming, first of all? Clearly branded terribly. Normal, what does normal mean? Because in math, there's like things that are normal to whatever, like perpendicular to, or normal just means this idea of normal. So think of normal as being slightly offensive, because there is no normal. Like in our world, there's all kinds of people. So to say someone is normal, what does that mean? So get offended because you're like, that's not real. And so the normal curve is, it's not very human in a way. And it says that, we can mathematically define, like, what is it? I wrote it down. I love these things. Like 34.1%. 34.1% in this first standard deviation range represents 68.3%. This is like, hey, you're normal because you're in the first standard deviation. Congratulations. And then when you're in the second, top, let's say this is height. Apparently, for human beings, where 5'7" is considered normal, and once you start getting taller, you start becoming like not normal. Kind of hurts, doesn't it? Or when you're shorter, you're like, it's not normal. Kind of offensive, right? But it's a useful tool. The problem with tools is that tools are like, they scale really well. So this tool is like lasted for like a couple centuries, drives so many things. There's all these tables of numbers tied to this thinking of a normal distribution, and it's pretty amazing. And the normal distribution is also normal because this all adds up to 1. 1's a really cool number in math, right? So if you integrate, I love the integral symbol. If you sort of integrate, if you add up every bit of that goodness, it's like a paper towel to soak up the normal curve, you get 1. So that's a wonderful number 1. Normal curve. So what you can do with normal curve is you can like generalize, and you can measure like how unnormal something is. Like how unnormal is that? Well, it's like 2 standard deviations from the mean. Whoa, that's like not normal. Or like, if you're like within like 1 standard deviation of the mean, you're like, oh, you're normal. So anyways, it's kind of like not like the Harry Potter sorting hat, but it's sort of like kind of puts you in a box of normal versus not normal. But like so much of our stuff is built on this. So it's good to know. So normal distribution, aka glitch. Also called the Gaussian distribution. It's a cooler word. If you've ever used like Photoshop, there's like Gaussian blur. Not the same. Pause. The normal distribution curve is the same as a Gaussian distribution curve, but it's not the same as a Gaussian function. You follow me? Let's repeat with me there. Gaussian distribution, normal distribution, same. Gaussian function, different. Much more general. Just sort of chapter back to the function thing, and you'll see it's more about a parameterized space, a function. Gaussian distribution, what you expect, look like that. Okay? It's also quite beautiful, right? It's also beautiful because if you've ever visited, or if you're a fan of Ray and Charles Eames, they have this exhibit called Mathematica that IBM funded in the 60s. And the way Mathematica works is it has all these cool physical instantiations of math. And there's this big machine. Whoa. There's this big machine where a ball falls from the top, and there's all these like pegs sticking out. And when it like hits a thing, it like, of course, has to kind of deflect. It'll go in one of 2 directions. Think of the coin toss, right? This direction or this direction. And then when it kind of like hits this, it also has 2 choices, like this direction or this direction. So basically, these balls, they're dropping and dropping and dropping and dropping. And then down here, below it, it has a display. And what does the display look like? Sort of zoom out with me. This is not like using some fancy graphics or whatever, but zoom out. And you would see all the balls dropping and forming this normal curve, right? So it's pretty cool. It says that it's like a natural thing. When you drop something into a multivariate system of independent actions, you end up with a curve that looks like this. And then what happens is you wonder like, whoa, like what is this curve? I thought it was just about normal, and normal's not good anymore because it isn't. It's not inclusive. So how does this happen? Is this like some kind of like freak of nature? Some kind of interesting thing that happens in nature? When you think about it, if you've ever like shot like a bow and arrow, is that what you call it? Archery? Sorry. You know, you gotta have a target. Oh, here, target. You know, and you like shoot the arrow and it's like, oh, over here. I'm like, oh, over here. Ooh, over here. You know, you kind of get the edges, but if it's like and the better you get and the more consistent you get this like, you start to get good at the bullseye. So if you took this distribution of arrows and look at it from the side, it would also look a curve like this, all right? You hit it off in the middle, and then you hit it off in the sides when you're not, this is more like, if you're an expert, you're always going to hit in the middle. And sometimes, maybe you had a bad day, you'll get it in the edges of the bullseye. And so it looks something like this, right? Makes sense. It's super logical. Another way to understand why this is logical, I'm going to end on the point that normal is cool, but not a good way to think of the world because it kind of distorts your reality. But when you think about how this curve, archery, well, this is my track of mine. It's Sunday, so it should be like, let's see here. This thing falls, this thing comes here. Live means you're slightly nervous when you're talking to people who might be listening. You can't like edit this. All right, so like this is coming. This is the normal. Let's try what I was going to say next. That'll help me jog my memory. Okay, so normal, things falling. Yeah, things falling. It forms a curve. I remember now. I made my dice. This is what this is for. Okay, so if you remember this thing here, if I like flip it, it's like once every 2 times, 50%. If I do one of these, it's 1 every 6. And what's super interesting is that if I have 2 dice and I wanted to guess, is it a 2? If I add them up, is it a 2? Like if it's a 2, that means it's gotta be like, right? Like 1, 1. If it's a 4, it's gotta be, well, actually it doesn't have to be one thing. It can be 3 and 1. It can be 1 and 3. It can be 2 and 2. If I wanted it to be like 10, it can be a 6 and 4 in combinations. But if I want it to be 13, can it be 13? 6 plus 6 is 12. No, it can't be 6. 12. So the point is that when you add up the 2 dice, it has a limit. It like stops at 12. But at some point, you know, when the dice are lower numbers and dice are higher numbers, what happens is some combinations are more scarce and some are more frequent. So this whole 1 over 6 equality thing just like breaks up. It's like, whoa, there's something just moved to like a not predictable 1 out of 6. It just has an uneven distribution. And if you had like 3 dice and you sort of spin them, whatever, it just sort of like shifts it. And just like this Eames example, it's kind of like each time the coin's falling, it hits something. It's hitting another kind of 1 dice, 2 dice, 3 dice, 4 dice, whatever. And so it breaks this sort of even pattern of 1 out of 6 combinations versus 1 out of 2 combinations. So it's pretty cool. Oh, that's what I wanted to tell you, because that's one thing I wanted to remember how much I love. Okay, so before we do the last thing, what time is it? Oh my gosh, it's 30 minutes. Sorry. Well, those of you who left, that's why you don't stay. It's a good thing. For those of you staying longer, welcome. Oh, thanks. I'll read your comments. I appreciate that. So mean, mode, median, right? 3 M's. I mean, like these 3 words, if you just get these 3 things right, you'd like, I'm going to draw like a muscle emoji. You can get so much right out of guessing well. So, review. Median is the average. You take multiple things and divide them by the number, like A plus B plus C divided by 3. We tend to like teach this all the time. But if you have like lots of data, the mean is so much better. The mean is like way better. Because when you have lots of data points, the median becomes less effective, especially if it is biased in a direction. The series is biased in a direction. So, more data you have, use mean more than median. You're going to love it. And lastly, mode really gets a kind of short shrift, but mode is the number that happens the often, which is neither the median or the mean, but that's a pretty cool one. It's a cool one because in 100 events, if 50 of them were the same, that's the mode, kind of want to know that, right? That's a significant thing to know. Mean, mode, median. Okay, please check that out. That kind of like got me really excited. Ending on, last thing I want to talk about is we talked about the normal distribution curve, also called the Gaussian distribution curve. It's pretty cool. But there's also what's called the power law distribution curve, which is also called the Paretian, not Parisian. Those of you who are French, I'm not being whatever, but maybe this is a French word, I have no idea. Paretin. And this says that something happens a lot, and then it kind of trails off as the occurrences increase. And why is this important? It's important because we love this Gaussian distribution curve because of grading. Like, I'm going to grade Tommy and Billy and Jane and Mary, and I'm going to find an average. And if you're at a company, everyone loves performance evaluation with the top 10%, keep them. The top 20%, ship them out. Or there's all this idea that you can tier people. But what's interesting is that the research implies, which I've got to believe is right, is that in any company or organization, you have this amazing small number of super high performers. And then you have this actually, let me rewind that. You have a small number of amazing people in this power distribution curve over here. And you have a small number of those who are lower performers. And oftentimes a low performer, hasn't been given a chance, or the timing is wrong, so give them a chance, is what I say. But then this part over here, and drew it incorrectly, is like the majority. This is like, there's a lot of people who are good. They're average and good. And again, that bad word, average, but they're not like super ultra high performer. They're not super ultra low performer. They're in a sweet of getting a lot done. And how do we honor this group the right way? Because this sort of like tier thing kind of assumes there's someone who's like average, someone who's above average, someone who's less average, and so you can like break them down into some numerical, remember my numbers, like 34.1%, whatever standard deviation thing. I like this representation because it says that you might be lucky to have super ultra high performers, yay. And you're always going to have some lower performers. That happens, right? But it's this group over here that gets so much done. How do you keep focus on them versus trying to tier the system? What's it called? Stack ranking? There's a thought there. People ask, is this stack ranking? It's a different philosophy. It's a little more understanding that we're not just balls that fall down some kind of Mathematica simulation, right? Wow. Okay, so I've got to figure out why my video keeps glitching. I will not be able to because I've tried so many times. I may just use a cloud streaming service and give up on my super high-tech overthought thing. But, that's how we learn. We try things, and once in a while you get lucky with people who listen in and want to be part of it. And so I just want to thank Adelet and Diego out there for being the audience. Hey, the Kiri, just sort of listening in and being a part of a little experiment. I stopped doing this because I don't have time to do it. And you all are busy too. I understand that. But I had someone on Twitter ask me why I stopped doing it. So I thought that was enough reason to do it. And here you are. And that's a validation that it was a good idea. So thanks. Have a happy Sunday out there, no matter what day. All right. AWS. Sorry, Diego. Something else. This is something else. But thanks for that tip. All right. Bye.